So let's think about circular motion and think about what we just saw. So this is for motion, curving motion, force toward the inside of the curve. If you wanted to, now notice this direction that he had to apply a force to make a ball go in a circle. You've probably heard the word centrifugal force, right? You've heard that. So centrifugal means it just means so centrifugal, away from, fleeing the center. So a centrifugal force would be away from the center. Is this a centrifugal force? No. There are no centrifugal. The net force to make something go in a circle is toward the center, not out, right? So that name is a pretty. If you find yourself thinking about centrifugal force, think again, because what you saw is what's happening. It needs a force toward the center of the circle to make it go around. Okay, so let's think about the other part of a circular orbit going in a circle, which is dp dt. So we were thinking about this half. So here's another case of going in a circle. The moon travels around the Earth. The orbit isn't perfectly circular, but it's close, right? So let's consider location A here. What's the direction of dp dt for the moon at location A? And remember how we're determining directions here. So we have this procedure for finding the direction of dp dt. We're expecting you to use it. You can draw it on paper, you can draw it on the air, or you can sketch it with your hands, but you do need to actually think about the procedure in order to get the answer right. So we're asking about the instantaneous direction of the rate of change of the moon's momentum here. Okay, well, it's not 98% somehow, although the most people say 7. So let's use the procedure, see what we get here. So here's our circular orbit. Here's the location of the moon. And so we have to take 2 locations on either side, here or there. And there's a little arrow, so it says it's going this way, so we'll draw an initial momentum P initial and a final momentum P final, equal times, and then to get a delta P, we have to put these vectors tail to tail. And we find that delta P is inward. And we see that as we take these closer and closer together, we're still going to be getting the same answer. So in fact, the direction of dp dt is indeed toward the center of the circle. Now, if you got it wrong, think about what you did. Did you actually use this procedure? Okay. So some people answered A, or 1, which is straight up. That's not dp dt. What is it? It's the instantaneous momentum, isn't it? That's the momentum of the moon when it's at location A. But the momentum and the rate of change of the momentum are different things. The quantity and its first derivative are not the same, so that's a different thing. Okay, so interestingly enough, dp dt points toward the center, which is, and what's the direction of the net force on the moon at this moment? The same, isn't it? It's due to the Earth. It's this gravitational force, so we've got gravitational force due to the Earth, and I'm drawing it just slightly offset so we can see them. And so here's our vector equation. The direction of dp dt, the direction of f net are the same. This is a good thing. And in fact, the magnitude should be the same too, shouldn't they? So I should draw them. And we'll find we can actually use this. Okay. So some turning motion is circles and some, but not all orbits are circular. And we looked last night for a minute at a VPython program that was actually showing us a non-circular orbit, like one that may look familiar to many of you after your lab this week. So here's some object orbiting another object in an orbit that looks like an ellipse. And it speeds up, it slows down. We can look at dp dt for the moving object. Maybe it's a comet. Okay, so the rate of change of momentum is always toward the inside of the turn. It's bigger when it can be bigger for various reasons. The direction's changing fast or the magnitude's changing fast. Either one will do it. And note that in this orbit, there's, except for when it's right here and right here, there's a component of the net force that's not perpendicular. So we should expect that dp dt also has some non-perpendicular components. So let's look at parallel and perpendicular components of dp dt, where we mean parallel and perpendicular to the momentum. So as it speeds up or slows down, there's a big component of rate of change of momentum in the direction of momentum, and then here's this component that's turning it. So both things are happening simultaneously here. Okay, so we can actually write the momentum principle then in two parts. And we'll write it down and then we'll sort of explore where this comes from. We can write down that we have a component of dp dt that's perpendicular to the momentum plus a component of dp dt that's parallel to the momentum, and that's going to equal a component of f net that's perpendicular to the momentum plus a component of f net that's parallel to the momentum. And not surprisingly, it turns out that we get dp dt perpendicular is the perpendicular component of f net, and dp dt parallel to the momentum is equal to the component of f net parallel to the momentum. So we can separate it this way, and this turns out to be pretty useful. And what we're going to be able to show is that we can calculate this component curving motion in any case, whether it's going in a circle or an ellipse or anything. This instantaneous component we can actually calculate analytically, meaning an algebraic solution, and that allows us to calculate some things about curving motion that are actually really useful. So where does this come from? Well, we're going to do a little math, not a lot, but just a little bit. Note that we can write the rate of change of momentum as the time rate of change of the product of the magnitude of the momentum and a unit vector in the direction of the momentum. So we're factoring a vector into its magnitude times a unit vector in its direction. We've done this before. And so this is a product. So we have to use the product rule to differentiate this. And so what we're going to get is two terms. We're going to get the rate of change of the magnitude of the momentum. So I'll write it actually, so it's just easier to see here. Rate of change of the magnitude of momentum times the unit vector in the direction of momentum plus the magnitude of the momentum times the rate of change of p hat. This is the rate of change of direction. So all we've done is use the product rule here. But notice this is the rate of change of the magnitude. So this is speeding up or slowing down. And that's in the direction of momentum. So this is this piece that's parallel to the momentum. This is dp dt parallel. This is the rate of change of direction. And so the magnitude not changing, direction changing. So this is this dp dt perpendicular part. So all we did was just apply the product rule to really get a differentiation. So what we're going to show here is that we're going to end up with, you know how to do this, so we don't need it on the board. We're going to end up with the following thing. We can that this perpendicular component, dp dt perpendicular, in fact, the magnitude is going to be expressible in terms of quantities we can calculate. The magnitude of the momentum, the magnitude of the velocity, and the radius of curvature. The radius of curvature of what? Well, this is the kissing circle that we just talked about briefly last time. You can talk about even an elliptical or complicated trajectory as at any instant having some curvature as if of the circle that's tangent to it. And so that circle mathematically is called either the osculating circle or the kissing circle. And we looked at it last time for our elliptical orbit, and it looked like this. So remember, the red part is that's just the path. At any instant, we can draw this green circle tangent to our elliptical path at that moment. And so now we have a bigger radius of curvature up here. Now there's a smaller radius of curvature up here. So this r in this equation is going to turn out to be the radius of the kissing circle. For a circular orbit, it's just the circle, the radius of the circle. For a non-circular orbit, it varies, and so that's what we're going to be worrying about here. And so how do we get this? We actually get it from a geometric argument that I want to show you very quickly. It's in the book. But the basic idea is this. If we have some path So here at some point, here's an object that's moving along some path, which is not necessarily a circle. So here's its path, but at this moment, there's this is the kissing circle. We're interested in it right here. We can calculate, we can graphically show that dp dt is equal to that quantity of the following way. So here's the center. We have, if we consider, we do just what we've been doing. Here's the momentum here. Here's a p, and we'll just look at the direction of the momentum here. So we've got p hat final, and here we've got p hat initial. And we can put these two things together so we can get a delta p. So here we've got p hat final. We've got, this would actually be easier to draw if I drew it slightly differently. Let's do it here, not because it's not valid there, but just because I'm going to have trouble drawing it. Let's do it right here, where it's just going to be simpler to draw. So we've got p hat final, p hat initial. We put these two things together, so here's final, here's initial. That's delta p hat, okay? And so we have okay, well, that's a triangle, and we can draw a different triangle. We can draw a triangle that's got a radius r of the kissing circle and another radius r of the kissing circle. And then, assuming we're taking this small, there's a straight side here, which is really equal to the length of this arc. Okay, so its length is going to be v delta t. That's how far this object traveled in a time delta t. And that's some angle theta. Well, these are actually similar triangles because p hat is perpendicular to r here because the momentum's tangent to the circle. And so this is a theta. And so if we just rotate this triangle, we're going to get a r v delta t here and a theta. So we can actually write a proportionality relationship here. Because they're similar triangles, the ratio of this side to that side is going to be equal to the ratio of that side to that side. So similar triangles, we get change in p hat over p hat final is equal to the speed times delta t over the radius of the kissing circle. And that's these are going to be magnitudes, of course. Well, the magnitude of p hat is just 1, so that's going to be the change in p hat over 1 is equal to that. And so just rearranging slightly, we're going to get delta p delta t is equal to the speed over the radius of the kissing circle, delta p hat delta t. And we just take a limit as delta t goes to 0, so we get the rate of change of direction here is equal to v over r. And so this perpendicular component, which was dp dt perpendicular, was equal to the magnitude of that was equal to the magnitude of the momentum times the rate of change of that. So we end up with dp magnitude of dp dt perpendicular is equal to the momentum times v over r. Now, to many of you, this is actually a familiar equation because at low, so what is this really equal to? Well, it's equal to gamma mv times v over r, or gamma mv squared over r. And at low speeds, that's just gamma's 1, so that's going to be mv squared over r. And that is basically, so what's v squared over r? Well, that's the acceleration. Perpendicular acceleration is going to be v squared over r, which is something you may have seen if you've studied physics before. So basically, we've got this perpendicular component of dp dt. This is the component that's turning it, is equal to gamma mv squared over r, or pv over r. When is this useful? Well, it's useful if you know the radius of the Kissing circle. You certainly know that if it's traveling in a circle. You might actually know it at some other times too. So let's see if we can use it to calculate something here. First of all, as a warm-up, let's just answer this question. Okay, Moon is traveling around the Earth in a nearly circular orbit at constant speed. This is a different question. We're at location A again, but now we want to know which components of dp dt are 0. Okay, so which ones do we not have to worry about? So think about the direction. You already answered a question where you said that you told us the direction of dp dt, right? So now think about the direction of momentum here, and think about whether that was parallel, perpendicular, or the same. Well, so what happened? Did you forget your answer to the previous question? So here's what we had before. We had location A, and the Moon's going around that way. And what did you say the direction of dp dt was at this location? Okay, so you said it was this way, so that's dp dt. And what's the direction of the Moon's momentum at this moment? Straight up. So here's P, and that's a right angle then, right? So dp dt is perpendicular to P here, right? So what's the magnitude of the component of dp dt that's parallel to P? 0, isn't it? Yeah. Well, the one parallel is 0. The one perpendicular is the whole thing, right? Momentum. That's what we've been talking about all along. This whole time we've been talking about dividing both force and the rate of change of momentum into two pieces, right? So we have F net is F parallel plus F perpendicular. We have dp dt is equal to dp dt parallel plus dp dt perpendicular. Perpendicular to what? Okay, that's the key, isn't it? Perpendicular to what? Where do we start? What are the things that could be perpendicular to? So here's here's an object, and we're just talking about its, so we're just talking about dp dt. So here's some object, it's got some momentum, and we're interested in dp dt parallel and perpendicular. So let's say at this moment, here's the rate of change of its momentum. What is there to take components parallel and perpendicular to? This is the only thing. We don't have anything else it could be parallel or perpendicular to. So we're talking about a component parallel to the momentum and a component perpendicular to the momentum. Right? Okay, so that's what we're talking about. Let's look at that program again. Okay, so the magenta arrow is the rate of change of momentum. We said this was the perpendicular component. That's the parallel component. Perpendicular and parallel to what? The momentum. The momentum at that instant. So we're using the momentum at that instant as the reference to take components. So you have to visualize the momentum, but you know what it is, right? It's tangent to the circle. Okay? So is this all right? Okay. Want to try that question again? So let's try it again, and or is there a question you'd like to ask before you try it again? Okay, so I think you're asking a question about the difference between an elliptical orbit and a circular orbit. A circular orbit is really special, and you probably, if you've done the lab this week, you may get a sense that it's actually not so easy to get a circular orbit. You got to get things, and so so the question is, so an elliptical orbit, we've got something going around in an ellipse, and at some location, here's the object's momentum. The rate of change of momentum, not surprisingly, is the same as the direction of the net force. So here's dp dt, and we note that there's a component of dp dt. We could write it as, here's a component perpendicular to p, and we'd have to add that, which is parallel to p, so those would be the two components. But in the case of the circular orbit, in fact, at every instant, it turns out, because, why is this not entirely parallel to p? Because the magnitude of the momentum's changing. It's getting bigger and smaller. In a circular orbit at constant speed, the magnitude of the momentum never changes, right? And so all it's doing is turning. So we have, so at this point, the magnitude of the momentum is the same. It's just turned. At this point, the magnitude of the momentum is this, not all circular orbits are constant speed, but talking about circular orbit at constant speed. In that case, yeah, dp dt, because we're always going to be taking two vectors that are exactly the same length and subtracting them, we're always going to get dp dt pointing toward the center, and it's always going to be completely perpendicular to the momentum. So that's a special case of a circular orbit at constant speed. Now, if it was speeding up or slowing down, that wouldn't be true. Then we'd need a component in the direction of the momentum. Okay, good. Other questions? Okay, so you want to try it again? Okay, so circular orbit, nearly circular orbit, nearly constant speed. Would this be an easier question if it asked what's not zero? So yes, momentum is always the reference. And so it's a little bit complex because at each location you have to think about the direction of the momentum before you can answer the question. Yeah. Okay, so now we're on the same page. See, that's one of the reasons these questions are good. We can tell we're not on the same page. So now we seem to be on the same page. dp dt is completely, in this particular case, completely perpendicular. And so there's the parallel component is 0. Okay, good.